Hey there, it's Shannon Matchick-Myers, and today we'll be looking at section 5.1, primarily 5.1.1, which covers spring and mass systems, free undamped motion. So the second little subsection is free damped motion, and then the next one is driven motion, and then series circuit analog. So there'll be 4 videos for 5.1. Groovy? All right, so in this section, we will see that forms of the second order linear differential equation, and this one's like with y as the dependent variable, we're mostly going to see x's, but it's the same format. You've got some constant times a second derivative with respect to time, another constant times that first derivative with respect to time, and then a constant times the zeroth derivative. And it's non-homogeneous. Sometimes it's homogeneous, and then you'll get some sort of initial conditions often. And this will appear in the analysis of a vibrating spring/mass system and an electrical series circuit. Terminology and physical interpretations are all that really change. The function g is called the driving function, forcing function, or input of the system. A solution y at t, like I said, we'll be using x at t a lot in at least the first couple sections of the differential equation on an interval I containing t equal to 0 that satisfies the initial conditions is called the response or output of the system. This brings us into 5.1.1, spring mass systems, free undamped motion. Hooke's law, we looked at this a little bit in chapter 3, I think it was. Suppose that a flexible spring is suspended vertically from a rigid support, and then a mass, m, is attached to its free end. The amount of stretch or elongation of the spring will depend on that mass m. So masses with different weights stretch the spring by differing amounts. By Hooke's law, the spring itself exerts a restoring force, F, opposite to the direction of elongation and proportional to the amount of elongation, which is denoted by S. Thus, F is equal to negative K times S, where K greater than 0 is a constant of proportionality, called the spring constant. The spring is characterized by the number K. So, okay, you've got the absolute value of the force if that's equal to the absolute value of negative k times s, then what will happen is you'll just get k, because k was greater than 0, times the absolute value of s. The negative is just the absolute of negative 1. So what does this mean? If a mass weighing, I don't know, we'll just make it up, 15 pounds stretches a spring I don't know, 3 feet? How about that? Then we would have absolute value of 15 would equal to k times absolute value of 3. And so what would happen? We would get 15 equals 3k. So k is equal to 5. And that would be in foot-pounds. Cool, cool? And so that is your spring constant. Groovy? Okay, so Newton's second law. Newton's second law provides the concept of equilibrium. Position. Or rest position, at which its weight, W, is balanced by the restoring Ks of the spring. Remember from chapter 3 that weight is defined by W equals to M times G, where M is measured in slugs, kilograms, or grams, and G is the acceleration due to gravity. So, depending on what you're in, this could be 32 feet per second squared, 9.8 meters per second squared, or 980 centimeters per second squared. The condition of equilibrium is that mg would equal to ks, or equivalently mg minus ks is 0. Assumptions. Mass on the spring is set in motion by giving it an initial displacement. An elongation or compression, and an initial velocity. The motion takes place in a vertical line. The displacements, this is where x will come in, x at t of the mass are measured along this line such that x equal to 0 corresponds to the equilibrium position, which makes sense, right? That's the at rest. And that the displacements below equilibrium position are positive. That's going to be the kind of weird part. The net or resultant force on a moving body of mass m is given by the summation of all these forces is equal to m times a, where a equals to the second derivative of x with respect to t is its acceleration. The mass vibrates free of all other external forces. And so we have free motion. Cool? Okay, so here's our, little equation that we'll be working with. We've got m times that second derivative of x with respect to t. This is going to equal to, so this will be our F1, our force 1 is the restoring force. So we would have negative k, and instead of just s, we're going to have that amount. Remember, x was the displacement, right, of the mass. So x plus s would be the total displacement. So this right here, this portion of it, is the restoring force. And the sign is negative because it's in the opposite direction of the motion. Cool? All right, now we also have plus m times g. M times g is F2. And that is the weight of mass, which always acts in a downward position, positive position. So this is the weight of the mass. And it always acts in a downward position, so it's positive. Cool? Okay, so let's see what we get next. All right, so then if I go ahead and I distribute that negative k throughout, I will get m times the second derivative of x with respect to t is equal to negative k times x minus k times s plus m times g. But what do we know about m times g and k times s? The difference between them has to be 0, right? So I'll rewrite it so you can see more clearly. And this right here is assumed to be 0. So you get a much easier equation, right? We're going to basically just get the mass times the second derivative of x with respect to t is equal to negative k times x. Groovy? Okay, so now let's just take a look at what we're dealing with, okay? So I'm not an artist, warning you of that ahead of time. So you've got, this rigid deal here that's holding the spring. And I'm going to give you 3 pictures. We're going to look at the spring at different amounts of stretch or elongation. So it's the same spring. These are just the holders. All right, so this will be the spring. Oh, that's not very good. Without any mass on it. Cool, cool. So then it would be just like that, no stretch to it at all. Now let's take a picture or look at the picture of the equilibrium position. This is where we've attached the mass, okay, but there's no initial velocity. So same spring, a little more spread apart because it's stretching, right? And so you've got some sort of, mass on there. And so this is our mass. And then, so what we have going on here is that this measure right here is L for the length of the spring. Okay? Now, we still have the length of the spring on the second version, right? So we still have L. But now we also have x equal to 0, which is that state of equilibrium position, right? And so what's going to happen is the amount of displacement is denoted by S. So this little measure here is going to be our S. Cool so far? Now, this will carry over. This is still our equilibrium point. But now, let's say we've got some extra stuff going on. So we've got some initial velocity. There's this oscillatory motion. So this will be stretched even more. And then we'll still have our little mass attached. Can't draw today at all, can I? Little deal. M for mass. And then, so now this distance here is going to be L plus S. Actually, bring it up a little bit. L plus S. That's going to go to here. Cool so far? And now this bit here will be the amount of displacement x at time t. Cool, cool? And since it's going below equilibrium, right? Below equilibrium, x is greater than 0. At equilibrium, x equals 0. Cool, cool? And this is when we've taken into account motion. This one here was equilibrium position, where we have m times g minus k times s is 0. Groovy? Okay. Now, differential equation of free undamped motion. So this is the same one that we had over here, but I took the k times x to the other side, so it's added and then it's equal to 0. So now if I go ahead and I, multiply both sides by 1 over m, then I will end up with that second derivative of x with respect to t isolated, and then plus k over m times x is still equal to 0. Now what we do is we let k over m equal to omega squared. And a lot of times these constants that were, or these variables we're letting them equal to, it's so that it works out nicer when we're solving the equation. All right? So that's going to give us the second derivative of x with respect to t plus omega squared times x is equal to 0. So we just have a second derivative in this one, no first derivative. Cool, cool? And then instead of the dependent variable being y, it is x. Independent variable is time. This equation describes simple harmonic motion or free undamped motion. Two initial conditions associated with this equation are x at 0 equal to some x sub 0 and x prime at 0 equal to x1. The initial displacement and initial velocity of the mass respectively. Sorry, I can't talk today. So, if x0 is positive and x1 is negative, remember, for x to be positive, it has to start above or below equilibrium. Beautiful. It starts from a point below equilibrium position with an imparted upward velocity, because remember, upward is in the negative position. So upward velocity will be negative. When x prime at 0 is 0, the mass is said to be released from rest. And so, if x0 is less than 0 and x1 equals 0, the mass is released from rest from a point, absolute x0 units, above the equilibrium position. Cool, cool? All right, so let's look at the equation of motion. So to solve this equation here, let's check out its auxiliary equation. So we'll have m squared plus omega squared is equal to 0. And then m squared will be negative omega squared. And so m1 would be equal to omega I, and m2 is equal to negative omega I. So your whole imaginary number is basically going to have no solely real term. All right. So if you recall, I'll just add in here, and alpha is equal to 0. So x at t is just going to be C1 cosine omega t, and we derived this in an earlier session, plus C2 sine omega t. This is the one where we used Euler's formula in the summation and all that good stuff. Cool? All right, so the period of motion is t equals 2 pi over omega. The number t represents the time measured in seconds it takes the mass to execute one cycle of motion. A cycle is one complete oscillation of the mass. So the mass moving from the lowest point below the equilibrium, which is positive, right, position, to the highest point above the equilibrium position, and then back to the lowest point. So we are looking at the length of time between two successive maxima or minima of x at t. A maximum of x at t is a positive displacement corresponding to the mass attaining its greatest distance below the equilibrium position. And a minimum of x at t is negative displacement corresponding to the mass attaining its greatest height above the equilibrium position. Either case is referred to as an extreme displacement of the mass. The frequency of motion is F equals 1 over T. Well, when you go 1 over 2 pi over omega, that omega is going to jump to the top and you'll get omega over 2 pi. And is the number of cycles completed each second. The number omega equal to the square root of k over m. And that comes from over here. Remember, we had let k over m be omega squared. And so omega is going to be the square root of k over m. And that's measured in radians per second, is called the circular frequency. Of the system. And when the initial conditions are used to determine the constants C1 and C2 in that exit T that we just found, the resulting particular solution or response is the equation of motion. All right, so we've got all of these little terms down and all these bits and pieces. So now let's look at an example. So example 1, we have a 20 kilogram mass attached to a spring. If the frequency of simple harmonic motion is 2 over pi cycles per second, what is the spring constant K? What is the frequency of simple harmonic motion if the original mass is replaced with an 80 kilogram mass? All right, so since these are in kilograms, we don't need to change, convert these to slugs. If you're given a measure in feet, you'd need to convert it to slugs. And I'll show you the conversion for that soon. So let's take a look at what all we have. First thing to do, right, is we have our equations. So we have m times that second derivative of x with respect to t plus k times x is 0, right? Well, do we know m? Yes, 20 kilogram mass, right? So let's put in 20 for m. All right. So now, dividing through by 20 to get a coefficient of 1 in front of that second derivative, we're going to have k over 20 as the coefficient to x. Cool so far? Now, let's take a look at some stuff, right? So we know that omega squared is k over 20, right? So omega is going to be the square root of k over 20. But 20 has a perfect square in it, so that'll be root k over root 4 times 5. So we can take that 2 out of that denominator. We'll get a 1/2, and I'll put that root back together again. We'll have k over 5. Cool so far? So that's omega. So let's see what else we need, right? We know that we're going to need to have the format of our result, remember, is x at t equals c1 times cosine omega t plus c2 times sine omega t. We solved it up there. So what do we know? Well, we know omega, right? Beautiful. So x at t will be c1 cosine omega t, and remember that omega was 1/2 times the square root of k over 5. We still have the t hanging around, times t, so this whole thing is the angle, plus c2 times sine, same omega, good so far? All right, now let's figure out what k is. Wouldn't it be nice to know k? So here we go, because we want to answer all these questions, right? So we need to find the spring constant k. So let's do another bit of work on the side. We found omega already. Now let's take a look at finding k. What do we know? Well, we know that is equal to, beautiful, 2 over pi. That's from here. But we also know that frequency is equal to omega over 2 pi. So if we equate 2 over pi to omega over 2 pi, then what's going to happen? We'll get 4 pi over pi leaves us with 4, and that's equal to what? Beautiful. Omega. So omega is 1/2 times the square root of k over 5. So continuing, we will have, multiplying both sides by 2, we'll get 8 is equal to the square root of k over 5. Squaring both sides, we'll get 64 equals k over 5. And finally, for k, 5 times 64 is 320 is equal to k. K is equal to 320, and then newtons. All right, so we found our k, right? Now, when you plug it back in, and when you plug k back in, what's going to happen? What will we get for all of this coefficient here to the t? Maybe we could clean that up. Well, if k is 320, right? 320 divided by 5 is going to be what? 64, right? So I'm looking here at the 1/2 times the square root of k over 5. Well, k is 320. So that's going to be 1/2 times root 64. Root 64 is 8. So we'll get 1/2 times 8, which is 4. So at the end of the day, what's going to happen? Our equation is going to be x at t is c1 times cosine at 4t plus c2 times sine at 4t. Groovy? So we were asked to find a few things, right? We were asked to find the spring constant, k. So that was our spring constant, k. We were asked to find... Oh, well, we went a little further, I guess. I'm going to go ahead and box this one. That's our initial, equation, general equation for the mass, this model for the spring. Now it wants us to go and say, hey, what happens to this model, right? So let's actually plug that in here. So we now have this new model is actually going to be the mass times that second derivative of x with respect to t plus 320, because we found k, right, times x is 0. So now when we change the mass to 80 kilograms, we'll have the second derivative of x with respect to t plus 320 times x is 0, right? So when we divide through by 80, we'll get that second derivative of x with respect to t plus, well, 320 divided by 80 is 4 times x is equal to 0. Groovy? Well, what is omega squared? Well, omega squared in this case is going to be 4, so omega is 2, right? Because the k divided by m is omega squared, and that was 4. So omega is 2. All right, well, let's go ahead and take a look at what we have going on. So we have our frequency. So now they want us to find the frequency for this. So our frequency is omega over 2 pi. Well, what's our omega? Beautiful. 2, in this case, over 2 pi, which will be 1 over pi. Okay, so when there is a mass of 80 kilograms, we have this other information. So the frequency will be 1 over pi cycles per second of a cycle per second. So that was one of the things that we were supposed to find. Just go through and highlight. So what is the frequency when the original mass is replaced with 80 kilograms? That's this answer here. And then just for fun, what would our model be? X at t is equal to C1 cosine omega t, omega was 2, plus C2 sine 2t. Cool? All right, so now let's take a look at alternative forms. These can be a lot easier to work with. So when C1 is 0, or non-zero, and C2 is not 0, the actual amplitude A of free vibrations is not obvious from the equation x at t equals C1 cosine omega t plus C2 sine omega t. So let's just take a look at this alternative form. X at t is equal to A times sine at omega t plus phi. All right. A is equal to the square root of C1 squared plus C2 squared. And sine phi is equal to C1 over A. Cosine phi is equal to C2 over A. And so tangent of phi, therefore, will be just the ratio of C1 to C2. Now let's verify this. So starting with x at t equals A times sine at omega t plus phi. Well, using the sum of angles formula for sine, we're going to get x at t equals A times sine at omega t times cosine at phi plus cosine at omega t times sine at phi. And so that right here is applying that sum of angles formula. Okay, so now continuing, x at t is equal to A times sine at phi. I'm switching things around a little bit. And that's times cosine omega t plus a times cosine at phi times sine omega t. If we drew a little picture, this would be phi, this angle, and then this across would be C1, C2 would be the side adjacent, and oh, lo and behold, the hypotenuse would be C1 squared plus C2 squared under a square root. Cool so far? And so that gives us what? That sine of phi is C1 over the hypotenuse, which is C1 squared plus C2 squared. And then cosine of phi at phi is C2 over the square root of C1 squared plus C2 squared. So plugging this in, we will have x at t equals a, which was the square root of C1 squared plus C2 squared, times sine phi, which is C1 over the square root of C1 squared plus C2 squared. And then we have times cosine omega t, and then I'll do the other one down here, plus this a, which is the square root of C1 squared plus C2 squared, over, times cosine phi, which is C2 over the square root of C1 squared plus C2 squared, and then times sine omega t. Sorry about the dogs, but look what happens. These divide out to be 1, these divide out to be 1, and we get x at t equals C1 cosine omega t plus C2 sine omega t. And so it's verified because that's what we started with, remember, in general over here. Groovy? Okay. Let's take a look at the second example, all right? So a mass of 1 slug is suspended from a spring whose spring constant is 9 pounds per feet. The mass is initially released from a point 1 foot above the equilibrium position with an upward velocity of the square root of 3 feet per second. So we want to find the times at which the mass is heading downward at a velocity of 3 feet per second. So we're going to use that alternative formula, okay? So, all right, so let's take a look at what all we have, right? So we know that m is 1 slug, okay? And the spring constant was given to us as 9 pounds per foot. So K is 9. Now the mass is initially released from a point 1 foot above equilibrium, so that's going to make it negative, right? That'll make it negative. And so that gives us that the initial displacement, x at 0, is going to be -1. Groovy? Now there's an upward velocity of the square root of 3. Remember, upward velocity is going to be negative. So x prime at 0 is going to be -√3. Cool so far? All right. Now we know omega squared is k over m, right? So omega squared will be equal to 9 over 1, which gives us omega is 3. Cool so far? Beautiful. So we've got all this wonderful information. So let's put it together. We've got x at t is equal to C1 cosine omega, which is 3 times t, plus C2 sine omega t, which will give us sine at 3t. And now we're going to need x prime at t, right? So x prime at t is going to be negative 3c1 sine at 3t, using that power rule, or sorry, not power rule, the chain rule, and then plus 3c2 cosine at 3t. Well, let's apply those conditions. So x at 0 we know is negative 1. So negative 1 will equal to C1 cosine at 3 times 0 plus C2 sine at 3 times 0. Cool so far? Groovy. So then negative 1 will be C1 times cosine at 0 is 1, right? Plus C2 sine at 0 is 0. So C1 is negative 1. Now, looking at x prime at t. So x prime at 0 we said was negative root 3. So working with that, we will have negative root 3 is equal to negative 3 C1 sine at 3 times 0 plus 3C2 times cosine at 3 times 0. Negative root 3 will be negative 3 times C1 sine at 0 is 0 plus 3C2 cosine at 0 is 1. So let's see. The first term zeroes out, and so negative root 3 over 3 is equal to C2. So now we have our equation. X at t is equal to C1 is negative 1. Remember, our x at t is C1 cosine 3t, so negative cosine 3t, and then minus root 3 over 3 sine at 3t. Groovy? All right, so here we go. Looking good here. Now we are going to, we're being asked, right, to find the times at which the mass is heading downward at a velocity of 3 feet per second. So we're actually going to write this in this alternative format, okay? So remember that x at t can also be written as a times sine at omega t plus phi. So let's figure it out, okay? Remember that a is equal to the square root of c1 squared plus c2 squared. So a will be the square root of negative 1 squared plus negative root 3 over 3 squared. So that's going to be, let's see, 1 plus a third, which is 4/3 underneath a radical. And so a will be 2 over root 3. Groovy? Now, we know omega. We know, now we have to find phi, right? So we find phi the different ways you can find it, but remember tangent phi is the ratio of C1 to C2. You have to be a little careful because, so we have tangent phi is C1 over C2. Tangent phi is going to be, include your negatives, so -1 over -√3 over 3. And so that means it's in which quadrant? Awesome. It's going to be in quadrant 3, where both the x and y coordinates are negative, right? So simplifying this a little bit, what are we going to get? We're going to end up getting tangent theta is equal to, you're going to get 3 over √3, all right? But then when you re-rationalize that, you're going to get tangent theta is equal to 3√3 over 3, so you just get √3. And that happens at a reference angle of, beautiful, pi over 3. We're in the third quadrant, so it's got to be 4 pi's over 3. And I'm sorry, I put theta in here when they should have been phi. So phi is 4 pi over 3. Cool, cool? So now, here we go. X at t will be equal to a, which is 2 over the square root of 3, times sine at omega we had from before as 3t, and then plus 4 pi over 3. Now we were asked to solve, when we want to find out the times at which the mass is heading downward at a velocity of 3 feet per second. So what do we need? Velocity means beautiful first derivative. So x prime at t is going to be, awesome, the 4 pi over 3 is a constant. Using the chain rule, we'll have 3 times 2 over √3, constants go along for the ride, and then cosine at 3t plus 4 pi over 3. And then we put x prime at t equal to 3, because that's when we wanted to find the velocity, sorry, can't talk today. We wanted to find the times at which the mass is heading downward at that velocity. So we'll get this going on. And then the 3's divide out. So we're actually going to get √3 over 2 is equal to cosine of all of this, 3t plus 4 pi's over 3. Cool so far? Well, at what angle is the cosine function √3 over 2? Beautiful. At a reference angle of pi over 6. The cosine function is positive when? Awesome. It's positive in quadrants 1 and 4. We've got a triple angle, so I'm actually going to go around a few times, all right? And then we'll get a general solution. So all of this stuff, this whole angle, 3t plus 4 pi over 3, has got to equal to pi over 6, 11 pi over 6, because that's the fourth quadrant angle that has a reference angle of pi over 6. And then each time I'm going to add 12 pi over 6, because that's 2 pi. So we'll get 13 pi over 6. We will get 23 pi over 6. And then we will get 25 pi over 6. And then 35 pi over 6. Cool so far? All right, now from each of these angles, we need to subtract 4 pi over 3. So the common denominator is 6, so you're really subtracting 8 pi over 6. So 3t is going to be negative 7 pi over 6. And then we'll get 3 pi over 6, 5 pi over 6, 15 pi over 6, 17 pi over 6, and then 27 pi over 6. And I just subtracted 4 pi over 3, which is equivalent to 8 pi over 6 from each angle. Now we need to divide each one by 3 and simplify. So the first one will get negative 7 pi over 18. Now the next one, what's going to happen? The 3 divided out some of that 6, so we're actually going to get pi over 6 for that second one. And then 5 pi over 18. This one, we can divide out some 3s, so we'd end up getting 5 pi over 6, 17 pi over 18. 3 divided out some of this one, and so we would get 9 pi over 6, which in turn, or 9 pi, over 6, which reduces to 3 pi over 2. So what we want to do is get a trend, right? Because this is periodic. So here, and the reason I went around 3 times is because I had a triple angle, all right? So here we go. Now, let's take a look at how much space is in between, certain angles here. So if I take a look at the first angle, and I'm looking at, okay, what's the difference between negative 7 pi over 18 and 5 pi over 18? So if I figure that out, 5 pi minus negative 7 pi, right, all over 18 would be 12 pi's over 18, which is going to be what? 2 pi over 3 in between them, right? So I'm going to try that. I'm going to say, okay, well, t could equal to negative 7 pi over 18 plus 2 times n pi over 3. And what'll happen is you'll get all of these that have the 18 as the denominator. Cool, cool? All right, what about the next, right? 5 pi minus 1 pi all over 6 is 4 pi over 6, which is again 2 pi over 3. So we're also going to get t is equal to pi over 6 plus 2 in pi over 3, and n belongs to the integers. Cool, cool? All right, and that's the solution. That's when we'll have that positive direction of velocity of 3. Groovy? All right, so that wraps up this video. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please click on the like button and subscribe. All right, take care. Bye.